Let's get our presentation started. As you see, this is the fancy talk. Everybody is buzzing about big data, data science. So in this talk, I'm not going to go into all the math that scares students off, but we're going to keep it interactive and fun. Right? So this is your buzzwords. You need to come up with ideas, and we'll discuss things as we walk through on what do you really mean by big data. You know that it's out there, but what does it mean to you? How is it in your life? Do you have to go to school to understand big data? Or what is it going to do to you in future, your career-wise? So let's get started. Big data. Let's start from you guys. So I'm sure you heard this word before. What do you think this means? From you, anybody? Lots of data, right? That's exactly what it means, big data, large data. And you see the definition. It's large volumes of complex data of any kind. And some typical examples is your Facebook, right? Think about your Facebook. Just look at your Facebook for a week. So you have your post, you have your likes, you have your videos, your watch, and the comments you made on somebody else's or something describing your life, your daily interactions, and maybe you watch some news, right? You'll watch some ads. Now, think about collecting that for a week. How much data do you think you would have? A good bit. That's just a week. Now, let's think about it for 1 year. And ever since you've had a Facebook account at all. Now, think about you having your data with everybody, like the friends in your classroom. How big is that? Think about all the videos, Facebook's posts, messages you send each other, right? Now think about a country. Think about the world. Facebook, we're not alone, right? Facebook is everywhere. Now think about that. How large is it? And now let's think about the nature of data. We talked about large, complex volumes of data, right? So just one data, what kind of data are we looking at? Like a mixed volume, right? It's not just purely images, purely voice, purely video. It is a mixture of every single thing. So now you realize why it's so complex. Now think about your Netflix. Now, one video that you watch, one movie, movies you watch in a week, movies you watched ever since you have had subscription, movies your friends have watched, right? So everything out there is a big data now. And in the beginning of big data was something like, okay, it's big enough, gigabytes is big enough. Remember all the memory things we talked about in class? So before 8 bits was big, and then when floppy disk came, I used to make fun of my uncle because he had this 1/4-inch floppy disk and I had the small one, and I was doing DOS programming, and I was like, oh, you did this big of a floppy disk? Look, I can put my floppy disk in my pocket. It has 1.44 MB. That was big. Right, 1.44. I always like to stress, do you know it has 1.44? I can fit it in my pocket. Now think about the flash drives you have. You can put it in your keychain. You can have about 125 gigs or even terabytes like Passport, right? So of course the technology has evolved, but so has your data being generated and how you want to process the data. Again, if somebody else you want big data is, this would be the technical definition, or at least something you can point to for reference, saying when you generate data at high velocity, variety, volume, and there are two more now, which is value and veracity. So we'll look into what that means. So initially back in 2001, this was the formal definition. So if you're given a data, you would say it is a big data if it has high volume. That is data density, accumulated over time, just like we discussed. Your Netflix data, Facebook data. And velocity. Think about transmitting all those data, right? You send your friend a message, and your friend is traveling somewhere in Europe. And you collect all those messages you've sent across a year to different people. And think about all the transmissions you do, your emails that you send, or posts that you do, and things like that. High-speed data, you're communicating with people all the time. Variety of data, the third one. That is data nature. We talked about post, audio, video. It is a mixture, right? It is not just one kind of data we are looking at. It's a mixed variety of data. So with that comes the fourth V, that is veracity. That is data integrity. I'm looking at all these big volumes of data from Facebook. Fake news. That is your fourth V literally over there. Now I'm watching all these news. There's an Apple News, there's BBC News, CNN, Fox News, fake news, and all these kind of news is out there. How do I know that the data I am looking at is trustworthy, right? So let's say I sent you something, or I wrote an article of news, but how do you know that really happened, right? So that is the big problem that we're facing. There's so much of information out there. You can read an incident, and you can read an incident, and you can read an incident, 3 incidents about the same talk. But 3 of you are saying 3 different things. The talk happened in tech hall, the talk happened in SSP, the talk happened in Frank hall. So who is the 4th person going to trust? So where do you know where you have to go, right? So you notice that that is your 4th problem, and the 5th being value. So the 4 things are what you want to do with data, properties of data, and the last one is what are you going to do with it? Right? Now you have all these videos, you're talking about Facebook posts, what do you want to do with it? That is where your value comes. As far as Facebook is concerned, can anybody tell what their value was? Cambridge Analytica. Maybe we should not go over this and talk, but that's pretty much what it is. How can you make use of this data to come up with some transformative application? Something that is worth it. All the trouble of going through all this data. Interestingly, when you see the diagram, you see the volume is this densely packed cube, right? It's pretty dense. You have all kinds of data in there. Velocity just means it's fast-moving data, real-time transmission and things like that. Variety, it's a mixture of data. Veracity, how do you trust data, right? Now I send a circle, how do I know if I send a circle or a star or a hexagon or something that the user sent? If I'm Netflix, I sent you a movie. But how can Netflix make sure that the movie transmitted to you is the movie you're watching? Or the movie that you asked is the one that Netflix is sending to you, right? So that's your 4th one. And value is here. So academia, that's me. Industry, people out there in Huntsville looking, who are looking to hire you guys. So that is where your value is. Notice I have 2 different values, because as far as big data standpoint for academics is concerned, the value for me is solve new problems, right? There are so many applications out there, so much of challenges out there and how to work with big data depending on the domain you come from. So my task is how can I solve those problems through research, right? Whereas in industry, that's not the thing. They're not out there to solve the problems. They're out there to make money. So their take is, how can I solve the problem that my consumer is interested in? How can I solve a problem to attract more consumers, make money, keep them interested, and keep my company growing? So that is where the values differ when it comes to industry as well as academia. Challenges. I like to say this is fill in the blanks after high. So we talked about velocity, variety, and all those things. So what kind of challenges do you perceive it to have? If you're running it in your laptop, neural nets. That's right, formulated properly. What else? Remember we were talking about neural nets? So what happens when you run big data on your neural net? It needs high performance, right? So the first challenge is storage. Do you have enough storage to store all the data? Right? So what is big data? Remember I started off from gigabytes, now it's going from terabytes, petabytes, exabytes. How much data do you have? Think about all the data Facebook is collecting, right? So the next one being transmission. How many of you have taken networks communication of some sort? So you guys do know that you have limited bandwidth, like when you're transmitting, downloading movies and stuff like that, you have limited bandwidth. Now, if I try to bombard you with all this big data, and if I'm trying to transmit all these things and run something in the network, transmit packets of big data throughout, what do you think is going to happen to my network? It's going to slow, might even kill it, depending on how big of a packet volume I send, right? That is similar to what you use for cyber attacks, by the way. So again, transmission is highly dependent on the volume and velocity attributes of big data. The next one being computation. Remember the neural nets that we talked about? So this is the example I like to give in the class. So let's say you're doing 10 samples of data, 10 data points, and all you're doing is you're calculating a matrix, right? You want to find an affinity matrix, or just multiply one to itself, multiply 2 matrices, 10 data points, A and B. So what is the resultant size of your net data? Let's say a square matrix 10 by 10, because you started off with 10 data points, right? So your matrix multiplication should lead you to 10 by 10, let's say. Now, let's say your A is not 10 data points, but 10,000 data points. What about now? 10,000 times 10,000. Now 100,000, 200,000, 500,000. So I'm not even converting this into bits and bytes in the form of gigabytes, but notice that suddenly you have this huge amount of matrix sitting there, and guess what? Good news is you haven't even started doing what you want to do with it. Right? So that is where computation comes in and memory issues comes in. You have fixed RAM, right? We talk about this in computer science all the time. You have fixed RAM. So if you have this big of a matrix sitting in your RAM, what are you going to do for the rest of the computation? Right? It scales up pretty quick very soon. And this is a really neat thing which I like, which I pulled out obviously from the internet. You guys can find it too if you Google. But this is neat because it shows you the differences between each field. So beginning of the beginnings, when things started, you had a definitive field like signal processing, then came around image processing, then came around AI and all these things that derive from each other. But now, everything is a big family of methods. And that's exactly what this diagram is depicting. So notice that when you go to business school, I've had some talk with business school folks, and they have their own data science and analytics. But business analytics is completely different from computer science. Right? Because they are looking at predictions, trades, stocks, and forecasting, and those kind of techniques that they usually call, their big data analytics. But when you come to computer science point of view, you're using deep learning, neural nets, and you're also talking to machine learning techniques and scaling it to a larger level, artificial intelligence. So everything is, together. It's like this big family talking to each other. One derives inputs from the other. And notice the data comes in and your inside of the value gets out. So you have this big black box, and it's up to you as a user what you can do with the black box and get the value you want. Right? The key point you want to remember is big data is driven by value. Right? So you have all those 4 attributes, but at the end of the day, you want to answer what are you going to do with it and why do you want to put output. Okay, so deep learning, since Tristan was interested. So this is what I would like to say your recycled neural networks. Right? So back when neural networks started, you had one input layer, one output layer, one hidden layer. So you had limited processing power back 20 decades ago, 2 decades ago, not 20 decades. So you had limited processing power, and just like we talked about the floppy disk, right? So that was the kind of memory you were looking at, and you couldn't scale up. But now, given the advancements that we have, we can easily add more processing layers or hidden layers to understand more about the data. Right? The best thing about big data is you have a variety of information you have to draw conclusions from. But before, you could not use up all the information you had because, did not have good enough computers, did not have good enough memory, and all those things. So that is where deep learning comes into place, where you can plug in all those, use all those big data values and get the output you need. Now let's talk about cool things that you can do with it. Right? So this is where the topic gets more interesting. The first one is my area of research, remote sensing. Simplistically put, satellite images. Right? Think about the weatherman who predicted snow and you did not have snow. So think about him. Of course, he can come to wrong conclusions, but we want to make sure that we arrive at right conclusions using remote sensing. Right? So the key point, what you see on your right, is sensors. So your weatherman is predicting something. So where does he get that information from? Data, satellites, right? You need some mode of getting your data, right? Remember, your photographs, your camera, your cell phone is also a sensor, which takes photographs. The same way, if you want to take photographs of space, you have satellites, right? So that is your satellite imagery right there. And also, you notice that you have drones, because now you don't really have to depend all the time on satellite data. You can always port your sensor on drones and just fly over the area, field, university, and have a map. It's as easy as that, right? You do not need giant sensors as you would have before. And once you have acquired your image, because the whole point of a big data is you start with the data, right? So now you have acquired your data, you have some means of calculating, getting the data, then you have this data that looks like this, a giant cube, right? We talked about it being dense, high volume, and stuff like that. When we talk about your cell phones, right? You have color photos. Do you think it's just made up of this one big square color photo? Yes? Think about black and white versus your color. What do you think is the difference between your black and white and color? Of course, my photograph is colorful and it's more fancy and nice. Huh? RGB, very good. That's what I was looking for. So notice that the photographs that you have, maybe mine, whatever, selfies that you take, they are not just one image, but it is a cascade of 3 different images. So you have a red image, a green image, and a blue image. So what you're seeing is a composite image, right? So for example, you have green. So you get green via a combination of red or yellow, red, green, and blue. So you're having some kind of influence from all these, bands to get your composite image, whatever you're taking, right? So that is your camera. You have 3 different bands coming in to give you a composite image. So let's look at the satellite, hyperspectrum. So before, RGB had 3 spectrum, right? Everybody has heard or learned about electromagnetic spectrum in science, right? So you know that you have all these different wavelengths, and we are operating in the visible wavelength, red, green, blue. But if you go to hyperspectral, it just means that it's not just 3 anymore, but you have like 100 to 200 slices of the spectrum. Isn't that cool? So now you're looking at the same image from 100 different viewpoints. And each of those 100 different viewpoints or 200 different viewpoints has different information for you. Right? That is the cool thing about hyperspectral data or the satellite data to make it more easier. And when you plot it, let's say I was looking at the chair, the blue chair, right? So if I try to plot the blue chair, what do you think my graph is going to look like? Is it going to look like all blue? Silver and green in there? That is right. And what is the basic principle about reflection? The color that you see is not the color that it actually is. Everybody remembers that? It's the same about grass is green and sky is blue, right? So the color that you see is not actually the color of the material. Yeah, we all agree to that? And that is what you see from this. So let's say you want to plot some trees. We expect it to peak at the green, right? I mean, the trees are green. Of course, it should peak at green. But what you see is your peak is not at green, but more like infrared. So this can be thought of as your fingerprints, right? How your fingerprints are unique to you. Your signatures, how these materials react to different spectrums, right? Different light bands is its signature, spectral signature. That's how the spectral signature comes in. Okay, so now I've acquired the image. I know it's a big volume. I'm trying to understand what I'm looking at, trying to see what kind of materials it is, what are the things in my image, and I have like this, big spectrum of signatures literally, and what do I do with it? I put it in my computer and do whatever I want. That's where the application processing, your big data analytics, data science, machine learning, talk about all the jargons you want, that's where it comes, right? So far all you've done is a simple procedure. You acquire it, and you take it, you understand what it has, put it in a computer, and then when you get your number cracking going on. This is just an example of how you would start your application from scratch if you are generating your data. Most of the times you already have the data, you start working with the data and arrive at some kind of conclusion. Okay, now that we have come so far, what kind of applications do you think we can do with satellite data? Critics know? And hopefully UH will close down and get a snow day. Right? So besides that, what kind of applications do you foresee? That's right, drought, that's a very good one. Anything else from the pictures that you see? That's right, disaster relief is a very good application, in fact. Because think about this, hurricanes, oil spill, and all those applications. Sometimes it's humanly impossible to go there and estimate the damage that happened. But can a drone fly over and capture the images everywhere that you cannot go? Right? Can you get satellite images from the places you cannot go? Right? So you can go to the places where you could not go before because of technology. It's cool, isn't it? So once you have some kind of image, you can start from there and find out what are you looking at, what kind of information you need, what is the extent of damage done, like disaster relief, and how can I check it? Can I let people know that there are some people stuck over here, or this is the place that is worst hit and others do not know about it? Right? Because you do not have access to every place in case of disaster relief. And think about somebody like in farming. He has acres and acres of land, and he wants to know what is the concentration of pesticides he needs to spray. Right? So one thing he can do is walk over and check his plan and check the plan and decide how much he wants to spray here or spray there. But if he has hundreds of acres, do you think somebody can manually walk through and decide different ages of crops and different kinds of crops, let's say, and then decide what you want to spray and where? Not really. But here, you can fly a drone, get the image, and you can use that to even predict diseases. Like your GMOs, corn, you want to test and see if they have some early disease. They do not, because you cannot see it by eyes, but it'll have a different reflectance from the healthy ones, right? Let's say the leaf is yellowish, whereas the healthy ones have green leaves. And you don't see all the leaves, but Guess what? The drone sees it. Right? Isn't that cool? So these are some of the cool things you can do. Military, again, has so many applications, detecting explosives, mines. You want to help the soldiers in the battlefield, right? You want to find all the stealth vehicles. How can you find it if it is hidden from you? So tons and tons of applications in remote sensing out there. And what I work with is how can I use these satellite data to come to those kind of conclusions depending on the application. Okay, so when you see results like this on technical papers, you would see something like this, where this is an Indian Pines data. You're looking at different kinds of crops, by the way. And notice that when you run your algorithm, what happens is all these areas should be solid colors, but they're not, because the solid colors is what it really is. But when you run it and try to guess what kind of crop is in there, what kind of age it is, and things like that, you see different spots, which is telling you you predicted wrong. Right? So those are the misclassifications. And basically, you want to say, okay, this area is my method where it has improved. Notice that I do not have much misclassifications here, but over there, I do have some different colored spots. Right? The different colored spots means that, so let's say for the right area, all of this crop was a particular kind, but I have predicted over there that the blue spot happens to belong to some other kind. So I'm saying that, let's say if this is corn, I predicted the other one was soybean, something like that. Right? So those are the misclassifications that you would see. This is a crop field, and one of the challenging data sets because it's difficult to distinguish between different kinds of plants. Right? So this is how you would see some of the results, and when you run your algorithm, what you're trying to do is how well I can predict, how well I can come to conclusions and identify the things I'm looking at. Right? So this is remote sensing application. And I wanted to introduce you to different kinds of technical topics and then some fun projects. This is another research in cybersecurity, right? So this is something we just hardly ever think about. How many of you remember the smart grid virus that crawled in and shut things down? Yeah, yes, no? So think about it this way. We're all becoming more smart, right? We're all connected to each other. And now you have everything up on the grid, smart grid. We like it to be that way. You have sensors to monitor the dams, pressure, bridges and everything, test train, all those readings. But you're doing that because you don't want a human to go out and scout for it, right? So think about all the remote places your pipelines run through, your oil pipelines. Right? If you watch James Bond in the movies, you know that they're really huge and wide, and somebody can get inside and do a lot of things, bad things. But now you have all these sensors to make sure that things are not, as bad. And if there is any problem, leakage, fracking, you can let somebody else know. So you have all these sensors out there. But that also means that you're not sending people regularly to check on those sensors. Right? So one thing is they can be physically hacked. Somebody can just go and do something with the sensor itself if it is not protected. And the other thing is you can hack it if it is wireless communication and stuff like that. Right? So that is where the question comes, how are we going to protect all these things, our national infrastructures? Right? Think about dam. If somebody blows up a dam, what kind of destruction can it lead to? Somebody shuts down the power grid, what kind of chaos it can cause, right? Or even if it sends out the wrong information, nuclear power plants, right? If a virus gets into that program, you're not going to be there where the radiation is going to be. And you will want something smart and intelligent to monitor it. And if the sensor goes bad, somebody hacks into it, you are going to blow up a whole nuclear plant, right? So that is where how you can come up with smart techniques to make sure that you can protect the attacks while it happens then and there and protect the rest of your network from it. So one of my methods was just prune the network. If you sense there is something wrong with the data pattern that's coming in, you shut the node down and protect the rest of the network. Most of the time what is done is you do a centralized networking, so you have to get information from all of your nodes, all of your sensors. Think about smart grid. You're waiting to hear from your 100 sensors in your smart grid. But sometimes, by the time you wait for the information from 100 sensors, you might already have an attack, right? So what we are doing is let's start off with not just centralized, but per node kind of, some analytical methods. The challenge with this is, what are we dealing with? Big data, right? But these sensors are there because they're compact, portable, they're easy, and they're not intelligent. And now I am just refuting what I said, where I'm trying to make something that's not intelligent. But Does this really have the capacity to become intelligent? Does it have all the computation memory resources to even do these intelligent things? Right? Because if I'm asking you to check right there, it cannot really do it. So that's a real challenge where I have to come up with some real-time analytic techniques, which is lightweight and it does what it has to do immediately. You can do, balancing out sometime later. But this is just a view into what kind of cybersecurity kind of applications you would have, intrusion detection being one of them. This is a neat project from last fall. This is called Instapark. Hopefully we will have the app by the end of this semester or next. This started when UH did the zone parking, right? Everybody was hunting for parking and nobody knew what zone it was or where the spot was. So one of my students came to me at the end of the class and said, Dr. Menon, I want to do something about it, right? Let's come up with a smart parking application to solve our parking problem. So we were like, okay, let's do it. And we started off by pulling a data set, parking data set, pkloud data set, and what we did is we cropped all these different cars. Remember, if you're doing like neural nets or any kind of images, you need to start by getting your data, right? So we want to make sure that how can you detect a car from an empty spot? The whole chaos was because you were looking for an empty spot and you eyed a spot and somebody else got it. And now you have to hunt for another one maybe miles away. So this is what we did. We cropped some data, empty, cars, and we did some edge detection, some data learning to find out how it looks like. How can we detect an empty car from a full car? Put it into neural nets and did some magic, and finally we could detect the cars from the empty spaces. About 80% is where we are, and we piled some more intelligent learning, and as of the semester, it's about 98%. Right? But the whole challenge is can we deploy it on cloud so that you guys can download it and access and get a real-time stats. We're still working on it, but this is a really smart application. This tells you that big data does not always have to be like super fancy or super attractive. It can also be some realistic, simple problems, which is attractive in its own, right? Think about everybody's life and all the people who would think if this app came out. Right? So this is just the kind of impact you can make with your big data. Something more fun. This is from my biomedical project or computational biology. I included that because I want to make sure that you guys understand or learn about one or the other application from different domains and realize that big data is not just one thing. Right? So this is actually a cancer application, or Alzheimer application. And when I started this project, I really did not know what big of an impact it can make, because what you hear about mostly in social media is people dying with cancers. Right? We all know when we hear cancer, it's like, oh my God, that's a really dangerous thing. Right? Bless you or whatever, whatnot. Express our thoughts and prayers and sympathies or support, whatever it is. Right? But we know when we hear cancer, it means bad. Right? It's big bad news. But nobody talks about Alzheimer's. Why? Because first of all, who are the people who talk more often on social media? It's us young folks. And we are not affected by Alzheimer's as of now. Right? So by the time we realize that we are affected by Alzheimer's, it's already an old man problem and nobody wants to look into it much more. Right? And what shocked me was when I looked at the statistics by Alzheimer.org, about 5 million folks in the United States have Alzheimer's. It's one of the 7th leading diseases that kills people. And it kills people more than breast cancer, prostate cancer. But guess what? Nobody talks about it. Right? So, and it's shocking that more men are affected by it than women. Oh well. So let's start with why this project is or what big data can do with it, right? Okay, so there are some tiny protein fibers in our brain called microtubules. They're made by polymerization of alpha beta, polymers as you see. And these are these tiny ones like in your neurons and so on. So what they keep on doing in your brain is recycling. So you have this free pool of proteins, they attach to one end, they start growing, and after some time, they disperse on the other end, that's called shortening, and the other one, starts recycling and regenerating and so on. This process is mostly like a cycle. There are microtubules growing, there are microtubules shortening, right? The shortening ones disperse molecules into this free pool, and those go into the growing microtubules. What you need is a healthy mix of microtubules in your brain for, good functionality, especially in case of neurodegenerative diseases. And this process of randomly switching between your growth and short stage is called dynamic instability phenomenon of microtubules. You have this, this microtubule right there. It's switching randomly. There is no certain length where it says that I'm going to stop or it's going to grow. It switches randomly between growth and shrinkage, growth and shrinkage. And why this phenomenon is important is because notice the shortening. What can happen to it? What happens if it just keeps on decreasing infinitely? It can disappear. And now you have a shortage, right? So that is where your neurodegenerative diseases comes in. So sometimes the microtubules that become short, they do not grow back again ever. They just disappear from the pool, right? So now you're lacking all these microtubules. So what we looked at is, okay, we are looking at a cell like this. How can we estimate growth and shrinkage rate and maybe predict Alzheimer's early on? Because by the time Alzheimer's kicks in, the symptoms are already out there, it's evident, it's irreversible damage. You cannot grow back these things, right? So is there a possibility that we can look at these signals or images and find out early on by looking at the patterns that maybe this person is more susceptible to Alzheimer's and start some treatments early on to prevent the damage, do damage control more of? Right? So that is what this project was looking at. And it was pretty interesting because nobody talked about Alzheimer's, and when I read all about Alzheimer's, I was like, oh my God, I did not know it was like the 7th leading killer disease in the United States. So this is just how you can make a difference. Again, Alzheimer's is just one of the diseases, but you can make a difference in cancer, any kind of diseases out there. The next, movies. How many of you watched Aquaman? I saw Aquaman everywhere on Facebook, and I was like, God, is it so famous that everybody watched it, and I was the only one who did not watch it? You did not watch? Okay, great. I do have somebody. So one of the things what we do is look at social media for reviews, right? Okay, a friend watches, somebody else watches it. How popular is this if everybody's talking about it, right? We get curious, and that's how we go and watch movies. But how about it if there was an intelligent way on how we could just chug all these reviews together and decide who is right and who is wrong? And remember the fake news thing? There is a lot of reviews out there that is just out there to grab your interest, right? It's not worth your while. So how can you do this? This was from my big data class, by the way. It's a real project done by a student. It was pretty interesting. So what he did was he went to IMDb dataset, got all these reviews, positive, negative reviews, and he chugged in and he was like, okay, if I have to watch this movie, tell me whether it's worth it or not. And he used a neural net basically to do it for him. And I thought that was pretty neat. But who would have thought that you can actually go watch your movies based on data science, right? Isn't that cool? Yes, no? Right? Just go to your friend and say, whoever did this, say, hey, I want to watch this movie. Tell me what you think about it. And he's going to pull all the information, reviews, and tell you whether you want to watch the movie or not. But this is some of the fun applications that I like. Another big one, Black Friday sales, again pulled up by a student because he wanted to analyze what is the trend for Black Friday and why do people actually buy, and what are the studies. He wanted to draw some conclusions about the Black Friday. Maybe I should have done Valentine's Day because that's just coming about right around the corner. But Black Friday. This was a Kaggle data set, and notice I put some things about the data. But the whole goal was to predict the purchase amount of the user. Right? How much you're spending, who is spending, why you're spending, what is selling mostly out there, and giving all those, company all their money. That's an interesting study, so I'll go more into it. The first thing he did was distribution study based on age. So I'm not sure if you can see it, but notice that that's the age versus the purchase amount. Which range has the highest purchase amount? That is right. And why do you think that is? 26 to 35. That's right. First of all, they're beginning to get children, or they're just new, young professional, a lot of money to spend. Or some young and single folks, they're like, I have money, all the money in the world is flourished. So I'm going to buy everything I see and save a lot of money in my Black Friday sale. Wait a second, did I say spend a lot of money and save a lot of money in Black Friday sales? That's exactly what this is. You spend a lot of money, and it's mostly 26 to 35. And notice that 36 to 45, the graph actually dropped drastically. What happened in just 1 year? You get more established, so you should have more money to spend, right? Well, that's true, but what other thing do you think, kid? That is right. So that is the age you're mostly looking to settle down. So either you have kids going to school, you're buying gifts, and sometimes you have a lot of stuff from your previous things that you don't need, and you're like, what am I going to buy? I have almost everything I need. Or sometimes you're running into financial issues, and you're like, oh, do I really need it? Do I not? Right? So notice, these are the cool kind of conclusions that you can come up with just studying the data, right? Which one? Yeah. That's true. That could also be a thing. But other thing being 18 to 25, it's mostly the school age. So it's not really you who is spending, it's more like your parents are spending. Right? So it's kind of a little biased. Now let's look at the bottom one. So it is the average age, versus your count of buyers. And again, your 26 to 35 has the highest count of buyers. Right? Most of the buyers are in that age group. You want to buy more things. And here is another interesting one, gender versus marital status. So look at how much the unmarried folks spend. Right? You see this big jump, I am single, I can buy whatever I want, I can own the world. So most of the time you go and burst out your money. But the same thing, married status is pretty high because now you have your kids, your family, you want to buy gifts for everybody, and Black Friday is one of the best ways to buy for Christmas. Right? Now look at total spending versus gender. This is a very interesting thing. Like the class was like totally shocked. And most of the students are like, no, that's not true. Who spends the most? Man, why do you think that is so? That was a very good one. Shopping one time in the only year. And guess what? So now if you tell me I can, although this is kind of a stereotype, but that's kind of true. Is if you ask a woman to buy, give her $10, $100, she'll make sure she get at least 10 back from those $10 or $100, whatever. But if you give a man $100, he might come back with a piece of coin or a wallet or a knife or something that was really fascinating or so. It just depends, So sometimes it's all about what kind of things you choose. So think about a flat screen TV, right? Versus me buying a new dress. So which is going to cost more? That is if you grab the very first, TV you see in the Black Friday sales right outside Walmart, and you have to fight and you might lose a tooth or two at the end of the day. But pretty much you notice that it's not just because of the gender, but it's also about the quantity and the quality of stuff that you guys invest in that makes us study more interesting. But anyways, I put it here, like especially all the graphs and stuff, because I found it very fascinating, and especially the whole class, you're like, oh no, it's not men who spend the most. But again, if you spend in electronics, easily buying a new laptop or something is going to cost you so many more, hundreds of thousands of bucks compared to buying anything else, right? That's an easy spend. This one. This is my favorite project out of our big data class. I have many others, but I really had to put this in there. So I put it in here for two reasons. First of all, I'm sure in social media you guys have come across all these games that people introduce. Find your past life, find your soulmate, especially for your Valentine, right? Find your soulmate, your matching bird sign, find your spirit animal, your spirit whatever, your best character, your love of your life, whatever, whatnot, right? So how do they do it? What are they doing when they do, all those games and questionnaires and stuff? Of course, this is more advanced than what they're doing, but let's say we make a fun thing out of the big data saying, find your spirit dog animal, right? So what the student did was she trained the data set of different frogs, dogs, as you say, I said frogs. So she trained it with all kinds of dog images. I don't know why I'm saying frog. And then she cropped the input image and found out different qualities. And this is just some things to show you what kind of layering you need to do. The thing being, see, if a dog is standing, you see the dog is standing. But does the machine know the dog is standing? My favorite quote of the day, especially for machine learning, is what you say is different from what the computer sees. Right? Remember, your computer is not seeing and processing information like you do. When I see a dog, I know it is a dog. But how can you make the computer recognize when the dog is standing, sitting, sleeping, rolling, no matter what? I have no confusion in my head that's a dog. But can the computer see that too? Right? So that is why we do all this kind of learning, to make sure that you take the image and view it from different angles, pick up different information to make sure you can detect this is a dog and exactly what kind of a dog, no matter how it is given to you, right? So a bunch of pictures of different kind of dogs. By the way, anybody has a favorite breed of dog? I see some smiley faces. Huh? You? What about you? You like labs, so there you go. So we on labs. Okay, so what she did was she trained some pictures. So she put a son's photo, and the software actually told her that this human resembles a dog breed, Old English Sheepdog, and that's the thing. And then if you train different images for different people, it gave you different dogs based on your signature, based on your dog's signature. And if you put input like Mickey Mouse, the software is supposed to tell you this is not a dog, right? So this is not a dog or human. So remember, all these constraints are the one that you programmed. But then again, let's take a moment. Now, this kid is nothing like Old English Sheepdog, right? Why do you think the computer or your neural nets even predicted it as Old English Sheepdog? It was trained in dogs. Remember, the whole goal of this application is find your spirit dog. But how do you think it does it? That is right. Very, very good. That's exactly what happens. It's all about your face, right? So as human brains, you're like, oh, this is a human, that's a dog. But what your computer does is calculate all the features of the dog and see what this human being matches the most close to. Find like this end set and pick up the first set or the second set or the third set and things like that. I can give it, tell me, I can ask it to tell me the first 10 sets I'm matching. But this is just picking up the first best match. As simple as that. So remember what we talked about? What I see is different from what the computer sees, right? As far as the computer is concerned, this human resembles an old sheepdog. And notice if I put a lab in there, I'm glad I put the lab in there. So if you put a lab, it tells you this is a lab. It detects. And notice the dog is sitting, right? It's not like this clear, distinct standing dog where you can see all of its legs, tail, and everything like that. So no matter what kind of photo you give, you want to make sure it recognizes what it is. And the dog below is Havanese, so you notice that it's sitting. You cannot even see its face, not anything more than its face, but it was still detected. That's right. So it all depends on your input data set and what kind of data you train it with, what kind of features you extract to help it predict. And it doesn't mean that you're going to get everything right, but this is a cute little thing, right? This is the kind of thing that you see in social media. And this means that you can come up with your own spirit animal, your love of your life. You can, whatever you want to do out there and do some cutesy things, right? So this is just a bunch of different projects from the social media perspective, cybersecurity, let's say remote sensing, or biomedical images. Just wanted to give you a whole span of different applications that you could think about and explore, right? Big data is everywhere around us. The only thing is we don't realize how much of it is already in our lives and how much we are using, right? So hopefully this talk has helped you to understand about big data and like it a little bit more and try some fancy cute things out of it. Well, thank you for coming to the talk today. Questions? So what is